Okay, so now we're gonna start question two. Question two. Oh, okay, I didn't even. Here is question two. Well, it's like part A and B, right? So part A is an isosceles triangle ABC with AB and equals AC. Okay, so it's inscribed within a circle. So we're gonna draw a circle first, and then because it's isosceles, I should do this. And because it said like, oh my god, A is like AB, AC is equal, so B can be here, C can be here. A chord AD intersects BC at E. So basically there's a D point somewhere on this arc. So because it never said that E is at the midpoint of BC, I should put it somewhere else so I don't get confused, right? So we'll say D is here, and AD is look like that, and this point will be E. So now it gave us an equation for us to prove. So we'll have to prove that A at B squared take AE squared equals BE times CE. So basically, because we have AB, right? We see AB is this edge. AE is this edge. BE is this one right here. CE is this one. So we're gonna think and we're gonna say we're gonna focus on the right hand side because most of the lines are on the right hand side. So because D is out here, we're gonna connect D with B, D with C. So then basically, because we have AB and AE, we're probably gonna use this triangle with the bigger triangle as they're probably congruent. Rid of that. Okay, so we're gonna write A, B, E, similar, not congruent, similar to A, D, B. So first we're gonna say BAE equals angle DAB because they're shared. Or should I write common? Common. And then we can write about how this angle equals this angle, and because they're the same, this is the same. So we have to prove that EDB is equal to ABE. So we're gonna do that. So we can basically write how ATB will equal to ACB because of angles subtended by same arc. Okay, so and then we can write that ACB will equal to angle ABC because of base angles are the same in isosceles triangle. Okay. So basically, and then we have proven ABE is similar to ADB because of AA. So we're gonna go back to this equation and see what we can do to make it like that. So basically, this one equals that one. So then we can start with ratios. So because AB is squared and it's bigger than AE, we can start with AB, right? So we do want an equation that cancels out AB to get the other side for the two triangles we found. So I'm gonna write here. So basically, AB over AE, as because they're in ratio, the same thing. So AD should be over AB, because look, AB corresponds in the first one corresponds with AD. AE in the first one, these two corresponds with AB. That's the easy way to do it. But then we can simplify this. We can time AB to the other side, becomes AB squared, and then time AE to the other side becomes AD times AE. And since we know that AD just equals AE plus AD, we can put that into the equation to make AB squared equals AE plus ED times AE, because we want AE squared. So then it becomes AB squared equals AE squared, AE squared plus ED times AE. Then we can move AD to the other side. So it becomes minus AE squared equals ED times AE, which is what it was. Wait, what? Oh. BE take CE. Wait, I did something weird. Let's see. AE part is weird. AD times AE, right? So yeah, that should be fine, but we want BE times CE. How did that happen? We're onto this step, right? So DE times AE, which we know from the other one, from one of the circle theorems, is literally just AE times BE times EC. So we're doing it right. I'm just confused. E squared equals BE times C, BE times CE. Because how was it intersecting chords are in ratio, because this is a cycle theorem, and then we have proved it. I should have wrote this at the start, because obviously this is like two chords, and then you can literally just put CE times EB equals AE times ED. That was supposed to be the first step, and I didn't do it. But because it's like a circle theorem, yeah, okay. Cool. Part B. Diameter AB of a circle with center O extends to C. So circle again, and then AB can be here. AB, and then diameter AB of a circle with center O extends to C. O extends to C, and from C a line is drawn tangent to a circle at P. So C, you draw a tangent. That's not right. Okay, we just can't draw. That's good enough. This is P. And the line PT is drawn perpendicular to AB at T. So we're going to draw a perpendicular. So this is right angle, this is T. Okay. And then we have to prove that CA times CB take TA times TB equals CT squared. For this question, right, it's just like a bunch of cycle theorems. So technically you can just write all the equations out. So we do know that from the external point, it's the same as the intersecting chords or ratio thing. So we can just, we do know that AB times BC will equal to CP squared. Then we also know that this is a right angle triangle, so we do know that TC squared plus TP squared equals PC squared. And we have we need something that equals CT squared, which is right here, so we can expand this. We can have like a chord rule for this one, but I don't like it, so I'm not gonna do that yet. See if it's possible just with these two equations, because CT is on one side, I'm gonna bring it out, because PC take TP, and PC, so basically TP, we know that PC is equal to this one. We can put AB, BC in already. Oh wait, no, that's not right. It should be CB and AC, because that's how the external chords work. So we're gonna put that in, and this will put this probably correct, but we do need to put that, we do need to know that TA times TB will equal, oh yeah, because this is like the external point, so we can literally just say TP squared equals AT times TB, because it's the same circle theorem as this one. So bringing this into here, we will make this equation into TC squared equals AC times CB from the first part, and then it will be minusing actually. We're gonna minus this equation, so it becomes AT times TB, and kind of we just have to rearrange to get it into our initial equations. So it was CA times CB take TA times TB equals TC squared, and then we just proved it. Yay. All right, bye bye.